Hi everyone, in this video we're going to talk about how to change the amplitude and period of a graph, and you'll see that this is exactly the same as the idea as horizontal stretches and horizontal shrinks. So let's get started. If my function is sine of x and I want to do a vertical stretch of that function, remember if we want to do anything in the vertical direction, we're going to multiply on the outside of the function. So if I change sine of x to a sine x, this should be a vertical stretch by a. So let's have a look. If I put in the normal graph of sine of x, and then let's try 2 times sine of x. So here a is 2, and maybe I'll make that graph look like a dotted line so that we can, or a thick line so that we can see it. So here's normal sine of x coming in now. This is 2 times sine of x. So the intercepts don't change at all. I'm just pulling the graph upwards and downwards. So what changed is the height of a single wave. Now, what is that height? Well, we need to know what the maximum value of this function is and the minimum value. So let's think about it with our brains first. The maximum value of sine is 1. If we multiply the entire sine function by 2, then the maximum value of our new one should be 2. And our minimum, by the same logic, should be -2. So if we look at the table, let's set our table to be sort of nice. Well, here's my normal graph of sine. The maximum value is 1, and then it starts decreasing again. 2 sine x, the maximum value is 2, and I start decreasing again. And the minimum value is -2. So between the max and the min, that's a difference of 4, which means that a single wave, the height of that is just 2. It's half of the big distance. So what this means is we get a new amplitude, and that new amplitude is going to be a, because we just took sine and multiplied it by a. So here's what the picture looks like, just as a recap. Quick sketch. So sine, we know, starts out going up. We get this wave. It starts repeating itself at 2 pi, etc. And it has a maximum at 1 and -1. Now our new graph is going to have the same shape, the same intercepts, except it's going to be stretched. And the new amplitude is going to be a, because the new high point is going to be at a. So now let's think about the other type of stretch or shrink that we know, the horizontal variety. So to change something in the horizontal direction, we have to do something on the inside of the parentheses. So what we do there is maybe I'll multiply x by b. So instead of looking at 2 sine x, maybe let's look at sine of 2x, for example. So I'll get rid of the 2 sine x here, and we'll put sine of 2x instead. And check that out, and I'll make it bold again so we can see the difference. So here's sine of x, and here's sine of 2x. So we don't have the same intercepts anymore, but the lowest point on the graph and the highest point on the graph are the same. What we did is a vertical or a horizontal squishing, a horizontal shrinking. So how can we describe that in terms of our new notation or our new vocabulary? Well, if you look at a single curve of the graph, the old curve took 2 pi to complete, a single cycle. The new one takes half that time. So let's draw our example here. Here's sine of x. So we complete one cycle at 2 pi. Now if we draw in sine of 2x, we finish one cycle in half the time. Why is that? Because, well, we multiply all of our x values by 2, so the x values are moving much faster. Our curve is making its curves much faster because we sped up the x's. That's a way to think about it. So our new period, so the period of sine of 2x is pi, which is the same as the old period divided by the factor that we sped it up by. So I'll say that again. The new period is 2 pi divided by b, because b is the factor we sped up by. Sorry, I was blocking that. The new period is 2 pi divided by this b. We divide by b because we sped up by that much. So we move that much faster, it takes us that much less time. So here's what you need to know how to do. If my equation is a sine bx, then this will have amplitude a, because I stretched everything out by a, and it will have period 2 pi divided by b, because it completes a cycle b times as fast as it did before. So it takes 1/8 the amount of time that it did originally. So we'll look at just one more example. So let's say I have the function, and this works for cosine too. So let's look at it for cosine. So if f of x equals 1/2 cosine of, let's say, 3x, well, then the amplitude should be 1/2. And the period should be 2 pi over 3, because we can complete a cycle in 1/3 the amount of time since we're going 3 times as fast. So let's look at the graph. We'll graph both cosine and this function that we just came up with. So cosine of x and 0.5 cosine of 3x. And let's graph it. So here comes cosine of x. And here comes 1/2 cosine of 3x. So now, to complete a full cycle, our tulip, well, let's see where that point is. I'm guessing that it should go back to 1 at 2 pi over 3, because that's where we complete the period. So let's check that. We'll check the value at 2 pi over 3. We want to make sure we're on the correct graph. Okay. 2 pi over 3. And we're at 0.5, which is what the height should be because we squished it down by 1/2. So at 2 pi over 3, we've completed this cycle. So that's the correct period, and the amplitude is 0.5 because that's the height of a single wave, as we expected. So changing amplitude and period is just the same as doing a vertical stretch for amplitude and a horizontal stretch for period. And we can tell what the amplitude and period are from an equation like this, because the number in front represents the amplitude, and 2 pi divided by this number in the parentheses represents the period. So in the next couple videos, we're going to look at how we determine what the graph is from an equation. There's one more thing we have to add into this, which is translations. And then we'll see if we can figure out what the equation is from a graph. So that's what's coming up.